Hello, hello. We have 3 chapters to go. Chapter 19 on nuclear chemistry, we're going to start with today. Then next week, we'll cover chapter 5 on gases, and we'll finish up with chapter 6 on thermochemistry. But this is a pretty short chapter, so it'll just be all in one set of notes, one video. And so this video serves pretty much as Friday, Monday, and Tuesday content. And so um, on Wednesday, I'll send out a quiz for chapter 19, or I guess I won't send it out. There'll be a due date set for the chapter 19 quiz. Probably be due by the end of the day Wednesday. And on Wednesday, there'll be notes for chapter 5. And so chapter 5 and 6 are probably a little bit more difficult than this one. But yeah, this was a pretty easy chapter. So nuclear chemistry kind of is weird compared to all the other chapters. Some of the laws we've talked about no longer apply. I almost think of it as more nuclear physics because a lot of the substances that we've talked about and their properties, they break down when we look at nuclear reactions. So let's get into that. So what makes nuclear chemistry different is we have transmutation. And this is what the alchemists were trying to do. They wanted to turn other junk into gold, and we've already said, nope, turns out you can't do that. There are a bunch of failures. But here we're going to say, yep, you sort of can. So you can transmutate or change the identity and convert one element into another, or sometimes it's just changing the isotope from, say, maybe cadmium 112 to cadmium 114. So by far the most common type of nuclear transmutation, nuclear reaction, is radioactive decay. So this is a nuclear reaction that to get going, you just sit back and let it happen. These are spontaneous reactions. But it doesn't always happen. It only happens for radioactive elements. So they spontaneously break down. And we've mentioned this before. So something like radium, when we say it's radioactive, it will periodically spit out helium particles, but in doing so, as it gives away 2 protons, it then becomes radon. So it transmutates from radium to radon under what's called alpha decay. And now again, this is because the nucleus of this element was just really, really, really unstable. Now, all elements, once you get up to polonium, anything with 84 protons or more, those are radioactive. So polonium, astatine, radon, francium, radium, pretty much everything towards the bottom. So those are all radioactive because of their size. It makes the nucleus unstable and it decays as a way of settling down. Now, the other radioactive isotopes could be more rare isotopes of other common elements. So you wouldn't normally say carbon is radioactive, like a piece of charcoal, but most carbon is carbon-12, a little bit of carbon-13. But if you come across carbon-14, it is radioactive. It will transmutate spontaneously into nitrogen by spitting out today we'll talk about a beta particle. And so, again, rare isotopes. We'll talk about how the alchemists, they were trying to make gold. Well, we said you can't do that. Well, technically you can. You can make gold, but while most gold has a mass of around 197, there's some you can use particle accelerators to make gold-20. So it's technically gold, but it's radioactive gold. And so that kind of odd, weird isotope will be unstable and spontaneously decay. Now, if you don't have just a naturally unstable nucleus, the other thing you could do is you could take any atom, any number of protons and neutrons, and you could smash them together at incredibly energetic speeds. We're talking like over 50% faster, as fast as the speed of light. If you smash them together, you can then overcome the forces that would normally keep them apart. And so you can also have a transmutation reaction with extremely high energy collisions. So this could be naturally occurring, like nitrogen, this carbon-14, this spontaneously, this happens to get generated high up in the atmosphere where nitrogen in our atmosphere gets bombarded by neutrons being thrown at it from the sun. We should be thankful that we have an atmosphere that can kind of collect some of the radioactive energetic particles the sun throws at us. So that nitrogen can absorb a neutron and turn into carbon 14 and spit out a proton. So this naturally happens. And then this radioactive carbon will then undergo decay. Now, we could also do this artificially. So we could talk about particle accelerators where we might take bismuth and chromium and accelerate them faster and faster and faster and then smash them together where it's energetic enough to create new elements. So if it's not a radioactive substance, we can get a nuclear reaction if they're moving just incredibly fast. Now, again, these are not things we could normally do on a bench top. So this is not like heat them up in a beaker. This is, we need to get them moving, millions of meters per second and then smash together. Tiny bit of history in this chapter. So radioactivity was first discovered by Henri Becquerel. He was working with pitchblende, which is a uranium-containing compound, and he incidentally found that when his uranium was put up in a drawer, so encased, it caused some photographic plates to become exposed, to develop, where typically, if you've ever used an old camera, when you click the button, the shutter opens for just a fraction of a second, and it causes that photo paper to develop. Well, it could somehow make it develop, not even being in direct contact. And so he observed that this uranium compound or uranium mineral was emitting this weird form of energy. And he has this unit, the Becquerel, named after him. Now, at the time, they kind of thought they were breaking the law of conservation of energy because there seemed to be this new energy source that was just eternally, flowing out to pitchblende. And from what we knew, that wasn't supposed to be possible. And so a few years later, Ernest Rutherford, the gold foil experiment guy, his lab figured out that whenever you have something spitting out radiation, it wasn't free energy, it was at a cost. The element would be always transmutating. So the radiation was a byproduct of a nuclear decay, where in this case they observed thorium, which had an atomic number of 90, would turn into radium, which was only 88. So when things are radioactive, they're throwing out these dangerous particles, but at a cost of them converting into something else. Now, one of the most famous names, that I'm sure you probably already know, is Marie Curie. And so she was a Polish scientist who worked with her husband Pierre, and they helped work out how to quantitate the radioactivity of different elements. So much so that when they were studying pitchblende, which had uranium, she realized it was more radioactive per gram than just uranium by itself. And what that meant was there must have been other elements that were giving off radioactivity. And so she discovered both polonium and radium. And so polonium she named after her home country. And so she's the only female to have ever won 2 Nobel Prizes in 2 different fields. So she won a Nobel Prize in chemistry and in physics. And so her big accomplishment was working out how to measure radioactivity. And if we were in class, we would watch some of these videos, one about the radium girls. Here's one on just her and by herself, but we're not. And so there are links in the other attached notes that you can watch. Click with all your extra free time. Go do that. Maybe not right now, but later. Now, we know a lot about chemistry. We know that when we have a chemical reaction, we're just rearranging the atoms into something new. We know that they're really only electrons that are involved. Again, oxidation, reduction, covalent. It's all about electrons being swapped. And we've talked a little bit about how you can speed up a reaction with increasing temperature or concentration, pressure. We mentioned collision theory earlier in in the semester. And then they can give off energy. Again, you can have exothermic reactions. But for comparison, I want you to know a few different things for nuclear. First, you have transmutation. So one element can be converted into another. It's not just electrons. Every subatomic particle can play. Protons, neutrons, and the electrons. And compared to chemical, again, you can make a very large bomb with TNT, and you can hurt yourself or others with chemical explosives. But comparatively, nuclear bombs or nuclear energy is crazy more energetic, and we'll talk about why. Again, here you can see 46 million joules worth of energy per kilogram of gasoline when you burn it. But for the fission of uranium, 76 million joules per the same weight. Oh, that stuff should have came up earlier. And now, one thing is, collision theory is not an aspect of nuclear reactions. The rates are not dependent on their temperatures or pressures or concentrations or catalysts. And then finally, throughout most of the year, I've briefly mentioned isotopes. You needed to know that they had a different mass, but they're chemically identical. So for chemical reactions, we don't care whether it's carbon 12 or carbon 13. We just need to know that, okay, there are different isotopes, but for all intents and purposes, they act exactly the same because they have the same number of valence electrons. But that's not true for nuclear reactions. Instead, for nuclear, isotopes behave differently. So in this chapter, we will specifically say, yeah, we're talking about carbon 14 because it will have different nuclear properties than carbon 13 or carbon 12. So for example, here are 5 isotopes of radioactive polonium. So they're all polonium with 84 protons. So they would have the same chemical properties. However, their mass, the isotopes are different because of a different number of neutrons. So one way we'll talk shortly about measuring this is the half-life. So this is how long it takes for 50% of the material to, on average, to decay into something else. So for polonium-208, in just under 3 years, 50% of it will be gone, or at least it'll have been decayed into something else. If you add 1 neutron, or at least you look at polonium-209, so different isotope, same number of protons, but it's slightly heavier, the half-life goes up by 100 years. Again, so adding this 1 extra neutron makes it significantly more stable. It takes 100 years for the same amount to decay. Add another neutron, well, now the half-life is only about 1/3 of a year. Add another neutron, it only lasts half a second. Add another neutron, now we're talking 0.3 microseconds. So the radioactive properties of an element are very, very dependent on what isotope we're specifically mentioning. So throughout the chapter, you're not going to say, oh, there's a reaction with uranium. You're going to say it's uranium-238 versus 235 because they will have distinct differences between the two. So similar to previous chapters, we have atomic number and mass number. But one thing we're going to do different is we're going to refer to the atomic number as the nuclear charge. Again, in the words, again, when you understand the word nuclear as in nucleus, charge as in, hey, what's the charge in the nucleus? Now, typically, you only be referring to protons for the atomic number, but in this chapter, there's other things that have charge that can come into play in the nucleus. Some things that are negative, some things that are +2 instead of a proton's +1. And so we're going to still collectively add them up to Z, which will identify the element, but we're going to call it the nuclear charge because there's other things besides protons. Mass number is still the number of nucleons, so that is the same. So here are some elementary particles we've talked about. Now, we normally use this notation for elements to say, here's the symbol, here's the mass, here's the atomic number, but here we're showing it listed for each particular particle. So a proton either as a p, lowercase p, or h, which is a hydrogen, has a mass of 1 and a charge of +1. A neutron has a mass of 1 and 0 charge. An electron has a mass number of 0. It has mass, but it's so small, we're just going to put 0. And it has a nuclear charge of -1. Now, you can see this extra symbol here. This is beta, it's the Greek B. Now, we're going to have two different symbols. Sometimes it will be E, sometimes it will be beta, and we'll talk about that distinction in a moment. But this is when you have there is different ways you could come about these electrons. And so a beta particle is an electron that has been recently ejected from the nucleus. Well, what was the electron doing there? I'll tell you in just a moment. We'll get there. So these are the elementary particles we're pretty familiar with. But then there's a couple others. There's the positron. Now, this is not a particle physics class, but a positron is the antiparticle of the electron. All matter has what's called antimatter, and it pretty much has the exact same properties except the mirror image, or in this case, it has the same mass, but it has the opposite charge. So it's got the charge of a proton, but the mass of an electron. And so a positron is not something you normally see in a chemical reaction. You don't. However, here we're going to see some of the weird radioactive nuclear decays that can happen give off weird things like positrons. Another one we're going to see is the alpha particle. It has a atomic number of 2, so there's 2 protons, and an overall mass of 4, so there's also 2 neutrons. Now, if you look on the periodic table for what fits that description, you're going to see that is chemically equivalent to a helium ion, He plus 2. So, but we're not going to call it helium because much like the use of beta, alpha and beta are going to distinguish where these particles are coming from. So it's giving it its backstory, and that's going to have to do with it came from the nucleus and it was ejected. It was the radioactive particle that was being emitted. So these are all particles that could be could be fired to hit a particle to radioactively transmutate, or these could be byproducts. So these could be on either the reactant or product side. So next, we're going to look at the different types of decay modes, and the first 3 are by far the most common. First, we have alpha decay. Now, alpha was the first kind discovered, which is why it's starting with A, the Greek A, alpha. And here we see polonium emitting an alpha particle and becoming lead. So here is radon emitting an alpha particle and becoming, radium becoming radon. So in both cases, we're seeing the mass number go down by 4 and the charge go down by 2. So these alpha particles are chemically equivalent to a helium nuclei. Now, you don't normally find helium charged, but what's getting spit out is exactly 2 protons and 2 neutrons. So it technically has a positive 2 charge, which is shown right here, plus 2. And so that's one of the reasons why the alpha particles can be dangerous. Helium doesn't like not having electrons. So pretty much as soon as they get emitted from the nucleus, whatever it comes into contact with, it will immediately steal 2 electrons to pretty much just become a normal helium atom. And if that's you, if you swallow a piece of polonium, then those alpha particles are going to oxidize proteins and DNA, and that's a bad thing. And so you can get radioactive poisoning by being overly exposed to alpha emitters. Now, honestly, they're not the most hazardous, they're the least hazardous. Again, they generally only travel a few centimeters because as soon as they come into contact with the air, they're taking electrons from nitrogen and oxygen. The biggest hazard is when you happen to ingest them. And we'll talk about why might you be ingesting them And the short answer to that is nuclear fallout. Next, we have beta decay. With beta decay or beta emission decay, as we said earlier, a beta particle is exactly like an electron. Now, this is not an electron that is coming from an orbital. This is not oxidation. We're not talking about an atom giving away an electron that it had in some orbital. Instead, this is a new, fresh, baby electron that wasn't there before. So we're not talking about, this is not, again, particle physics. We don't have to know the details of quarks and leptons, because there was a time that, hey, how small can you go? It's the atom. And then it was, how small can you go? Protons, neutrons, and electrons. And then a little bit later, oh, wait, those things are made up of quarks and leptons, things that are even smaller. Now, you don't have to know those details, but I do want to mention that because protons and neutrons are made up of these different things, they can actually change when under stress from one to another. So in this situation, you have a neutron that is neutral, that is just, it's tired of being neutral. It wants to be more positive. So how do you become more positive? You get rid of the negative. And so shown here, here's a neutron that turns into a proton and an electron. So it breaks up into these two separate. Notice 0 is equal to 1 plus negative 1. 1 is equal to 1 plus 0. So if you add a proton and electron together, the properties add up to a neutron. Now, the proton sticks around. So notice in these examples, the mass doesn't change. Even though you're technically losing a particle, the mass of the electron is so small, it's negligible. So the mass number 40 to 40, 17 to 17, 14 to 14 doesn't change. However, since you're gaining a proton in this process, because the neutron is now positive, notice the atomic number, the nuclear charge, it goes up 19 to 20. So you have technically an element that is one further on the periodic table than what we had before. But the overall mass number doesn't change. Now, these ones are considered more hazardous than alpha, because if an alpha particle was like someone throwing a bowling ball and you can't throw it that fast or far, well, then the beta comes at being so much smaller, comes out more like a bullet. And so they have a greater ability to penetrate through material. Our bodies can handle small exposure, like thin metal, or your skin can certainly handle small amounts of it, but you definitely don't want to be overly exposed to this stuff. Oh, and that bell means something. I don't know. But yeah, alpha and beta are by far the most common. But again, why is it called a beta decay? It's signifying that this is not an electron coming from an orbital. This is an electron that was just born. It was newly created. So its origin. Fun fact, if you eat bananas, and it's not limited to bananas, but other plants that have potassium, there's a small amount of potassium-40 that naturally occurs. And in a banana, you have about 45 micrograms of potassium-40. So the more bananas you eat, the more radioactive you are. However, it's still such a small amount that I wouldn't worry too much about eating too many bananas. Next, we have gamma decay. This is one you've probably heard of. Again, when we discussed spectroscopy and the electromagnetic spectrum, we had this gamma radiation we said was the most energetic, where we have visible light, then ultraviolet, then X-ray, and then the type with the shortest wavelengths and the highest frequency was gamma. Now, so gamma, it is pure electromagnetic energy. It does not have mass, and it can go alongside other decay modes. But this is by far the most dangerous. You do not want to get hit with gamma radiation unless you want to turn into a big green monster. Well, actually, you would really instead get radiation sickness and probably die. That's the more normal thing. But this is the gamma symbol. But again, it's not always shown because it technically does not affect the mass number or the nuclear charge. There's neutron capture. So here the identity isn't changing. Cadmium can capture a neutron to become, instead of 113, 114. Um, and so some isotopes can do that. Then there's spontaneous fission. Now, this is what you generally have happen with really, really large, unstable radioactive elements. When we talk about particle accelerators, they might make some new element like agonicin 294, but it will then like instantly break apart with spontaneous fission, where it doesn't just spit out little bits of alpha particles or beta particles. Instead, it just kind of breaks into much larger chunks. And then finally, there's electron capture and positron decay. You don't have to know these in great detail. These ones are not nearly as common as alpha, beta, and gamma, but they do exist. Electron decay is like the exact opposite. Oh, sorry, electron capture is the exact opposite of beta decay, and positron decay is like beta decay, except it is positive. One way we can detect if something is radioactive is using a Geiger counter. So they detect ionizing radiation. Keep in mind, not all radiation's bad. We like this, we like visible light. We like microwaves. We like cell phones and Wi-Fi. Ionizing radiation includes X-rays and gamma rays. So that's stuff so energetic it can ionize your proteins and DNA, and then that's the bad thing. So the way this works is you have a circuit set up. Here's a battery source, and then here's a cathode and an anode. But notice they're not in contact. There's argon gas in between. Now, argon is a very, very, very stable element. It's a noble gas. You would not normally think of it as reactive. However, if you have ionizing radiation penetrating, it can be energetic enough to cause argon to lose electrons and become charged. And what can charged particles do? They can electrically conduct. So essentially, if there's radioactive particles coming through, it can make it conductive to complete the circuit and then have this thing go off to say, oh no, run away, it's radioactive in these parts. So that's called a Geiger counter. Some of the homework questions are going to look like this, where we want to balance them to balance nuclear reactions to figure out what particle we would end up with, or what type of decay. And the two main things to remember is that both the mass and the nuclear charge have to be are always conserved. That should be at times. So if you add up the number of the mass number on the left compared to the right, it will be the same. If you add up the nuclear charge on the left and on the right, it'll be the same. So we're going to try some of that. So here we would like to know, hey, what type of radioactive decay are we seeing when polonium-212 turns into lead-208? So what we do is we look, what was the change? Well, we see that the mass went from 212 to 208. The charge went from 84 to 82. So that would mean that we've lost a particle that has. So knowing that it lost a mass of 4 and a charge of 2, we know that is an alpha particle. So if we were to rewrite this, we could then use this alpha symbol, which we know is identical to helium, but we're not going to put helium because we're signifying it was newly formed. For B, we have a change of mass of 0, and 55 goes up to 56. So that is a difference of -1. So this particle, where it has a -1 nuclear charge and a mass number 0, we know as a beta particle. And so we have an alpha decay and a beta decay. And this is part of the class where I would normally ask you to, hey, try it yourselves. I don't know, this looks weird. Give me a second. So on the first one, again, you can pause if you want to try working these out, and then I'll do the big reveal. which is now. So Einsteinium and helium make something in a neutron. So 253 plus 4 is 257. We have one neutron. So whatever our unknown particle is, it has to have a mass number of 256. Now, that does not tell us the identity of what we should put for X. For that, we look to the nuclear charge. 99 plus 2 is 101. And when we look to the periodic table, we find that is Mendelevium. Here we see potassium is undergoing beta decay, but we want to know, well, what is the byproduct of that? So you need to know that the mass number doesn't change, so it's still 40. But if you lose a negative, 19 losing a negative 1 goes up to 20, which makes it calcium. By far, one of the greatest mistakes is people going 19 and negative 1 make 18, and then they say argon, but it's not argon, it's calcium. Because beta decay makes it go up, alpha decay makes it go down. Cobalt combines with the neutron to make manganese and something else. So 59 plus 1 is 60, and that is equal to 56 plus something. That something has to have a mass of 4. 27 and 0 is equal to 25 plus 2, and that would be the alpha particle. Okay, next we have 235 and 1 is 236, and then we subtract from it, we have 99 and 135. So that gives us a difference of 2. So a mass number of 2, but this is saying there's 2 of them. So really each X has a mass number of 1. And for the nuclear charge, we have 92 and 0, and then 40 and 52, which adds up to 92. So this is showing 1 and 0, that is referring to neutrons. So there are 2 neutrons released. Now, most of the time, a radioactive substance will not decay and then be automatically done. Typically, they'll give off a radioactive particle, they'll become something smaller, but still radioactive. And so they'll go through what's called a decay series. So in this example, thorium-232 undergoes alpha decay, but then that product undergoes beta decay, and then that byproduct goes under beta decay. So here we want to look at what are those consecutive substances. So for these questions, you need to know what alpha and beta decay are, and you need to know that it is losing these particles. So here's thorium losing an alpha particle and becoming radium. Then radium loses a beta particle and becomes actinium. Actinium loses a beta particle and becomes thorium. So every time you have alpha decay, the nuclear charge goes down by 2. Every time you have beta decay, the nuclear charge goes up by 1. Next, we have something turning into protactinium-228. So for this, we're going to add the alpha particle back in, and so it would have had to be neptunium. But then going further, protactinium, it's going to go up by 1 to uranium, and then it's going to go down by 2 for alpha decay, and you end up with another isotope of thorium. Probably the most famous of all decay series is the uranium-238, because it's the largest radioactive element that naturally exists. And so here we're showing the half-lives in different types of decays. And we talked about alpha, beta decay, neutron capture, positron decay, spontaneous fission. But if you look at these ones, again, the primary ones that you'll see are alpha and beta. The other ones exist, but these are way more common. Alpha, beta, beta, alpha, 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 beta, alpha, beta, beta, alpha, beta. And so it undergoes 14 decay steps until you finally end up with lead-206. Now, on this table, it's graphing the mass with the atomic number. And so you can see the alpha decays bring it to the left, and then beta decays bring it to the right. But alpha is where it actually gets lighter and lighter. So overall, what's happening is the nucleus is getting smaller and smaller and smaller and smaller, until it reaches a size that is stable. Now, speaking of stable, here is the belt of stability. It is showing all of the known elemental isotopes that are not radioactive. So it is the belt of stability. So it's plotting all of these protons with neutrons to find here are the non-radioactive elements. Now, it starts off roughly 1 to 1. However many neutrons there are, there's an approximate equal number of protons. But then notice what happens. As there becomes more protons, you need even more and more and more neutrons. So it scales higher and higher, where there's a bias towards the number of neutrons. Now, what this does is it helps us, it kind of gives us a viewpoint of why neutrons. Because we know protons tell us what element we're talking about. They give them their overall properties. And we know chemical reactions are determined by valence structure. But what's the whole point of the neutrons? And so we believe neutrons play a role in counteracting proton-proton repulsions, where we know positive like charges repel. However, in the nucleus, they're crazy packed closely together, ultra dense. And think of the neutrons as kind of being a spacer in between them to help minimize those charges. And so the bigger the atom, the more and more and more neutrons that's needed to help stabilize it. And you get to a point where all the way up to polonium, where it doesn't matter how many neutrons there are, it's still going to be radioactive. Now, we can also use this chart to kind of pinpoint what types of decay we might see. So if you have too many neutrons, if you're above this curve and there's more neutrons than protons, then you're more likely to see beta decay. If you have an excess of protons, then you'll be under the curve. This is where you might see positron decay, electron capture, or neutron capture. Alpha, beta, spontaneous fission, those are ones that happen at much, much higher masses. So super heavy isotopes. So there's a tiny little bit of math in this chapter. So half-life is our quantitative way of looking at how long it takes for something to break down. How radioactive is it? And so it is the length of time for a material to decay 50% away. So this is following what's called first order kinetics, where you go from half to 1/4 to 1/8. This is exponential decay. So I want you to know this is not linear decay. It's not going from 16 to 8 to 0. It's always half, 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 half. You get this line that approaches 0 but never actually gets there. You might have learned this word. It is an asymptote. So using half-life, the larger the value, the more stable it is. So uranium-238 can last, it's 4.5 billion years before half of it decays, where something like Rutherfordium-261 only takes 70 seconds. So shorter the half-life, the more radioactive and unstable that element is. So there's a couple problems we'll do with this. So first, we can work out how much will be left, or how long will it take for a certain amount of radioactive substance to decay. So 23.5 grams, how long until it's only 1.5 grams? So what we do is I'm gonna set up this table where at time 0, there's 23.5 grams, but at 28 years, one half-life, it gets cut in half. If you wait another 28 years, 2 half-lives, that gets cut in half. If you wait another half-life and another half-life, finally, after 4 half-lives, it's less than 1.5 grams. And so our answer is 112. Now, I wouldn't typically be setting up a table. I would normally just put in my calculator 23.5 divided by 2, divided by 2, divided by 2, divided by 2. And when I see that it takes 4 times, it has to cut in half, I would say 4 times 28 to get my answer. Here's a question. You should work that out. And yeah, you should work that one out, and I'll tell you the answer to that later. Or if you just email me, you can tell me your answer then, and I'll respond and say, yep, it should have been this. Another way we could work this is looking at how much would we have left in a certain length of time. So 21 minutes for thallium 206 to decay with a 4.2-minute half-life. How much of our 25 grams is going to get left over? So we do something similar where you need to know how many half-lives have gone by. So it's easy to just take a ratio, how long we're waiting divided by the half-life, which tells us 5. So 5 half-lives have gone by. So that means if we start with 25 grams, it's that divided by 2, divided by 2, divided by 2, divided by 2, divided by 2. Those are supposed to be times, but when I went from PowerPoint to Google Slides, it just didn't work. You can abbreviate that as 2 to the 5th power, which is also important if if it doesn't happen to be a perfect integer. If you got like 5.6, you could put in your calculator 2 to the 5.6th power. And we get our answer of 0.78 grams left. One fun application of this is we can carbon date things. We can see how long has it been since something has died. So carbon dating is specifically taking advantage of carbon-14, and it only works for things that are part of the circle of life. Things that either undergo aerobic respiration or photosynthesis, or somehow have to take in a carbon source, which is pretty much anything living. Yeah, it's pretty much everything living. So it starts up high in the atmosphere where 80% of our air is nitrogen, and as it gets hit by the sun, some of it transmutates into carbon-14. And so that carbon-14 is much, much, much less stable than nitrogen-14. And so it's going to react with what's around it. And what else is in the air? Oxygen. So carbon-14 forms carbon dioxide. And carbon dioxide, now heavy carbon dioxide, joins the biosphere. Plants, they absorb it. It uses it through photosynthesis to build up starches and other stuff. We eat those plants, or we eat food that has eaten those plants, and you absorb this heavy CO2. Now, throughout your life, you will pretty much have a relatively constant ratio of carbon-14 to carbon-12. However, when you die, the carbon-12 is stable. The amount stays exactly the same. But the carbon-14, being radioactive, it decays. And so when something is dead, they'll look at how much carbon-14 to carbon-12 is present. And the bigger that difference, the longer it has been since it was alive. So it has a half-life of about 5,700 years, a little less than 6,000. Now, I need to point out this technique, it has many limitations. You cannot date rocks. You can't date fossils, because the further you go, the older something is, if the difference, the sensitivity goes down greatly as you get closer and closer to this end. So generally less, we're talking a few 10,000 years of being able to date something. We're also not going to be able to dig up like your great granddad's dog and say, oh, it died in 1892, because the precision is also just with a couple decades. Don't go digging up your great granddad's dog. That's weird. Now, one of the weird things about nuclear chemistry is we break the conservation of mass law, where we said if all you're going to do is rearrange things, mass should be conserved. But here it's not going to be. And this is because of what's called nuclear binding energy. Now, this is the energy needed to break the nucleus that's binding protons and neutrons together. Now, they're held together by what's called the strong nuclear force, which is the strongest of all the known physical forces that we're aware of. And it takes a lot of energy to break that apart. So here's fluorine 19 with its mass. If you put enough nuclear binding energy in to break it apart to get 9 separate protons and 10 separate neutrons, the weird thing is when you weigh it, it's heavier. The separate parts weigh more than when they were together. Again, that should be odd. Normally, if you were to disassemble something and weigh all the parts together, it should be the same. But here, it's not. Now, we call this the mass defect. So it increased 0.1587 atomic mass units. Now, what's happening is probably we can explain it with one of the most famous scientific equations of all time that everyone knows, E equals mc squared. Now, this is the mass to energy equivalence. And what it allows us to quantitate is the change in mass, which is delta M. How much energy would that be talking about? So delta E is this nuclear binding energy that's either being put in or given off. Delta M is the mass either going up and down. And then there's C. Hopefully you remember that C is another universal constant. Its magnitude is 300 million meters per second. It is the speed of light. And so even if you take tiny amounts of mass change, times it by this huge number and square it, you end up with really, really, really big values. Now, these units probably don't mean much to you, so let's throw some conversion factors at it, and we end up with this. The nuclear binding energy required to break up a single mole of fluorine is 1.4 times 10 to the 10 kilojoules. This is on par with one of the first atomic bombs dropped in World War II. So it takes a lot of energy. Now, I put the box around this. You're not going to have to do any math with this, but that's what this equation tells us. It relates mass to energy. So again, in the short of it, these nucleons, they weigh more when they're separate. When they combine, they weigh less because some of the mass is given up as energy. And again, that's really the secret of why nuclear reactions are so energetic, is mass gets converted to energy. You don't see that in chemical reactions. So to finish up the chapter, we're going to look at just some examples of nuclear reactions, and we're going to categorize them into two types: nuclear fission and nuclear fusion. So fission refers to any time we have larger elements breaking down into smaller things. Radioactive decay, which we started with, that is a type of nuclear fission. As it spits out alpha particles, beta particles, then you're getting smaller stuff. Uranium is already radioactive, but we could fire neutrons at it and it will undergo spontaneous fission to get these really large particles given off, plus some more neutrons and a whole lot of energy. Again, to show quantitatively, if you were to take the difference in mass of the neutrons versus of the uranium and the particles, you could then use E equals mc squared to figure out 20 trillion joules of energy for each mole of uranium. Now, again, for comparison, if you burn a ton, 2,000 pounds of coal, it can give off about 50 million joules. Now, that's a lot of energy, but comparatively, we're saying a tenth of a pound of uranium undergoing fission can give off 400,000 times as much energy than a whole truckload, 2,000 pounds worth of coal. And for that reason, we like to harness it, and we do that with nuclear reactors. Now, a nuclear reactor pretty much just takes something radioactive and lets it decay. But to harness the energy, you surround it with water. And what that means is the thermal energy it gives off converts water to steam. Steam expands, and that can drive turbines. At that point, it's not much different than a hydroelectric dam or a wind turbine. So you use the heat of nuclear decay to heat up water to generate steam to turn turbines, and there you go. You got electricity. Now, It's a little bit more complicated than that. One thing you have to do is enrich your uranium. And when we say enriched, it means we need to isolate or increase the amount of 235 isotope. The greatest proportion is 238, but it's not nearly as energetic or radioactive as 235. So it costs probably 80 to 90% of the costs is generating enriched uranium. Um, Now, one thing we want to do is control these reactions. We don't want a nuclear bomb, so we use control rods. Things like cadmium and boron, they can absorb the extra neutrons that are given off to slow down the reaction. So if you want to stop a nuclear reactor, you pretty much push all of these control rods in, and it's kind of like spacing. Imagine a bunch of dominoes. If you don't want one domino to topple all the other dominoes, you space them out. And that's what the control rods are doing. If you've ever visited or driven past Nuke 1 in Russellville, I like to point out to my kids that it's a cloud factory because, again, that's what it's releasing is steam. It's not smoke or smog, it's just water vapor. So I have many videos linked for things on nuclear power. Some of them are about how awesome they are, and some of them are on the negative. Like, did you guys ever hear of Chernobyl or the 3 Mile Island incident or Fukushima? Or there's probably another one I'm not thinking of. So nuclear energy, it's when it's working good, it's fantastic. When things go wrong, it's kind of terrible. So you can watch some of the video links to learn more about it. But again, I want you to know the basics. That it's nuclear fission that is using the heat to convert water to steam to generate electricity. Again, one of the nice things is, again, you've probably heard that nuclear waste is bad, but to you know compared to burning fossil fuels, the waste just goes into the ground, or can get buried into the ground, and it doesn't take up that much space. Where the waste for burning gasoline, petroleum goes right up into the atmosphere, and that causes problems. But again, we're not going to get into all that. Submarines. This is just a more fun fact. Submarines, since the 70s, have been using nuclear fuels to be able to, stay underwater for a long time. Essentially, in the lifespan of the whole submarine, it never really has to be refueled. This pretty much means the only time they have to come up is to replenish oxygen for the people that like to stay alive. And yeah, there's a lot of this is just fun facts, but yeah, most submarines are powered by nuclear fission. Now, if you don't want a nuclear reactor, if you want all the uranium to undergo fission at once, you get a nuclear bomb. So they take advantage of chain reactions. This is where each uranium undergoing fission gives off 3 neutrons, and then those can give off 3 neutrons, and then those, and it just dominoes. Here's kind of what that looks like. It happens in just a fraction of a second. Again, you push it, it ignites one, and that ignites another, and another, and another, and another, and you get this exponential increase. The longer time goes, the faster, the more of them that are undergoing this type of decay. Now, one thing it takes for a nuclear bomb is a critical mass. So you have to have enough uranium or plutonium concentrated so that when one undergoes fission, it actually gets the others to maintain that chain reaction. If they're too spread out, then this will not be achieved. There's a nice video on the Manhattan Project you can watch below. Now, fusion, as opposed to fission, combines smaller particles into larger ones. Again, the best example is to go outside and look at the sun. If you've ever heard it's a big burning ball of hydrogen, now it is powered by hydrogen, but not the burning of hydrogen through combustion, but the fusion of hydrogen into heavier elements, and it also releases lots and lots and lots of energy. Now, this you don't have to know this chart. Nuclear. This is showing the nuclear binding energy. Essentially, the higher up on the chart, the more energy that can be given off. More energy can be given off as it undergoes either fusion or fission, and you actually can get more energy from fusion than fission. So you might be wondering, well, cool, we should make power plants that are powered by nuclear fusion. And we would love to do that. But there's some big problems. Nuclear fusion requires crazy high temperatures in the tens of millions of degrees. You know, the sun can do it because it's incredibly massive, and it can maintain those temperatures. But for us, it's really hard to get this to sustain. We've been able to do it. One video you could watch on the tokamak. It uses electromagnetic fields to produce a plasma that gets crazy hot, but we have not been able to get huge surpluses of energy. We generally find that to make this even fusion reaction happen, it takes just as much. We have to put in massive amounts of energy, and we just barely break even. So there's not like a huge surplus of energy we've been able to take away. But they've been working on nuclear fusion for 50 years, and they're going to. In one of the videos, it always talks about a joke that the running joke is that nuclear fusion is always 30 years away. So in 30 years, yeah, we're going to have nuclear fusion, and everything will be like energy won't ever be a problem. Another application of fusion is making new elements. You've heard of particle accelerators, atom smashers. They take advantage of moving things really, 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 really fast. So nitrogen 14, if you fire alpha particles at it, you can make oxygen 17. This was Ernest Rutherford again, the first artificial transmutation. Now, we find that these particle accelerators can be massive installations. Here is an underground a depiction of an underground tunnel. The largest one being the LHC, the Large Hadron Collider in Switzerland. It is a 17-mile long track. And you take a particle and you can use electric and magnetic fields to accelerate it faster and faster and faster and faster and faster and faster around until you get to a point where you want to smash them. And so when doing so, you can create new elements, new particles. And then most of the particles have very, very short half-lives. They don't exist for even minutes, hardly even like a second. But you can have an array of different instruments that can measure all sorts of stuff, and we can learn things about the universe. Here's a link below to look more about that. Here's another. This is just a table showing of these elements up to livermorium. What were the particles they smashed together to make them? So you can just kind of look at that. Now, what if we want a bigger bomb than an atomic bomb? So the first bombs from World War II used nuclear fission. When we say atomic bomb, it's using plutonium or uranium. But in the 60s and 70s, we developed thermonuclear warheads. And if you've ever learned about the Cold War, it was kind of some dark times. The bombs got bigger and bigger and bigger. So we also call them hydrogen bombs. Again, not that we're taking hydrogen gas and burning it, but we're getting it so hot that it fuses together and releases crazy amounts of energy. So fun fact, to have a thermonuclear bomb, you also have to have a tiny fission bomb. So you have to use something that can, like uranium, that can undergo fission, so a tiny atomic bomb, to get these fuels hot enough that they start fusing together. And so if you've ever seen videos, pictures of these huge mushroom clouds, then that's what you're looking at. So it blasts this stuff so high into the atmosphere that it hits some of the lower levels of the atmosphere, and it's almost like it hits a ceiling where the gases are more dense, and it causes it to spread out. Now, if the blast doesn't kill you, you've probably heard of this term fallout. That refers to all the different radioactive debris that gets vaporized, spread tens, hundreds of miles into the atmosphere, and then falls down over the local environment. So if you happen to breathe that stuff in, or it falls on your soil and then you eat crops that were grown in that soil, then that can be bad for you. So things that were alpha or beta emitters, you probably wouldn't eat them, but again, fallout can make a region of space hazardous for decades after because of this. And here's a good video on from Veritasium. You should watch that one. This is just another fun fact thing. Here's a link: nuclearsecrecy.com/nukemap Nagasaki. So you basically can take this website and um, pull up a Google map. You can pick a bomb and try different locations, and just it will show just how far it could possibly drop. Here, this is Castle Bravo. It's the largest one we've ever dropped. If you've ever heard of the Marshall Islands or the Marshall people that are highly populated in Springdale, this is the bomb that we dropped on their islands. And this video talks about it and shows some video. They basically say, we dropped it on the other half of the island. We thought it'd be fine, but oopsie, it turned out to be like 3 times more powerful than we thought it was actually going to be. Sorry about that. Here's some fun facts. You don't have to actually just read over this, but it's fun facts. Again, there's tons of uses for radioactive materials. Again, from killing harmful bacteria on our food to getting all types of fun scans. Again, if you've ever heard of a PET scan, it uses positron emission topography. So they give you something that emits positron particles, and it can scan for that. Or iodine, if you need to image your iodine, your thyroid, they'll give you iodine, and it goes to your thyroid and it emits beta particles, and then all sorts of fun stuff. And that's it. This is chapter 19 on nuclear chemistry. So again, this video serves for Friday, Monday, and Tuesday. And so on Wednesday, I'll post the next chapter stuff. Wednesday, I'll also send out the quiz for you to work on that day. So have a great, fantastic day.